Hey there, guys. Moving off into the second unit. Today we're going to be talking about solving linear equations, which is the 2.2a. So you don't really need to pay attention to this part. It's not there. So just noting that we will come back to 2.2 later, so there'll be like a 2.2b. Solving linear equations in one variable, something you guys should have a ton of experience with. Remember that your goal is to isolate the variable, get x by itself. And to do that, we use inverse operations, right? So that if it says multiplying, we're going to divide. If it says add, we're going to subtract. If it says square, we would square root. But we're looking at linear equations, so we don't have to worry about that today. To eliminate terms of the equation until the variable's alone. All right. This is where we get to talk about one of my favorite math phrases, which I'm pretty sure I've never heard anybody else say this, but when you're solving an equation, you should be using SADMEP. All right, so that when you're undoing those operations, you're using those inverse operations, you need to do them in the reverse order, right? So when we're simplifying, we use PEMDAS, right? How do I know what order to simplify an expression in? That's for simplifying, right? Well, if I have to undo all of that to solve, then I would have to do it backwards. And so when you're solving, you should be using SADMEP to kind of guide you. Like, what do I undo first? What do I undo second? So just keep that in mind. There are different types of equations as far as how many answers they might have. We've all talked about, we've seen equations that have infinite solutions. We've seen equations that have no solutions, and of course there are equations where x equals 5, like that's the answer, right? So those are just those are different types of equations. So an identity equation, is true for all values of the variable. So this would be like your infinite solutions type problem. A conditional equation is true for only certain values of the variable. So if you find out that x is equal to 2 or x is equal to -7, with higher order equations like a quadratic equation, you could have x could be equal to -2 and x could be equal to 5, right? So it could have certain values work. And then there's an inconsistent equation, which is true for no values of the variable. So this would be an equation that has no solutions. So, what do they look like? Why do they have infinite solutions? Why do they only have one solution? Why do they have no solutions? What's going on there, right? So an example of an identity equation would be 4x plus 7 equals 10x minus the quantity 6x minus 7. All right, so how do we solve this? Over here we need to deal with this first, simplifying this, right? You always simplify an equation before you solve it. So right now we're using PEMDAS to simplify this. There's nothing for me to do inside the parentheses. There's no exponents. So I'm looking outside of the parentheses for any multiplication that needs to be done. So a little -1 right here. I'm going to distribute that through there. So I rewrite the problem. So I'd have 4x plus 7 equals 10x minus 6x, and now it's plus 7 since that minus sign is distributing through there. Well, of course, on that, still simplifying, so did my multiplication, there's no division to do, so I'm looking at my adding, subtracting, so I've got some like terms to combine here. So if I simplify that right side some more, 4x plus 7 equals, 10x minus 6x is 4x plus 7. So why is it called an identity equation? Well, look at the two sides, right? They're identical. And so the idea, as we move to solving, if I wanted to get rid of the x's, get the x's all on one side, well, I'd subtract 4x's. And I know to subtract because that's a positive 4x, right? There's our inverse operation. And so those would cancel on the left side, and you'd be left with 7. On the right side, it'd be left with 7. Again, those two sides are identical. So what I recognize about this is that it gives me a true statement. All right, 7 is always equal to 7. So when you end up with a true statement like that, that's always true, that lets you know that the real answer to this is that there are infinite solutions. The answer is not 7. The answer is that all values of x work. There's no number that I could plug in that wouldn't end up working, so it has infinite solutions. visually, what that means is that if I was going to draw this, right, these are linear equations, so that means their graphs would be lines. If I was to graph them, just this is not what they actually look like, but one of the lines would look like this, and then the other line would be right on top of it. Right? So they're always touching, they're always intersecting, so they have infinite solutions. So that's what an identity equation looks like. That's why it has infinite solutions. The x's cancel each other out, and you're left with a true statement. Conditional equation, only true for certain. So here's an example of a conditional equation. 12x plus 4 equals 8x plus 20. 12x plus 4 equals 8x plus 24. There's no simplifying to do, so I'm going to go straight to my SADMEP. There's no, so I want to do any addition subtraction first, so I want to gather my x's onto one side. So I'll subtract 8x, of course. Since I'm moving the variables to the left, I want to move those constants the other way, so minus 4, minus 4. So on that left side, I get 4x. On the right side, I get 20. And of course, dividing by 4, we find out that x is equal to 5. And so, right, there's our certain value that the equation is true for. Right? Only when x is 5 is the equation true. And so, what would that look like if I graphed it? So again, linear equations. So if I graph that, I'd have one line. Maybe it comes over here. And then I have another line. What this value is telling me is that they intersect at 5. So over here at 5, wherever that is, right, the lines would cross. And they don't need to be perpendicular or anything. I just kind of drew it that way, but just that they would cross at that one point. So they have one place where they're equal. That's the value, that's the x value there. And of course, I could find the y value of that point by plugging 5 into one of these two things, and it would tell me the y value of that point. So that's what a conditional equation looks like, algebraically and graphically. And then the last one, inconsistent, so we should end up with no values that work. So again, looking at this equation, noticing I need to simplify this right-hand side first. So I'm going to do some distributing. So I get 8, good Lord. Try that third time. Well, I don't want blue though. It's not struggling. Struggle's real. Driving that struggle bus. So 8x plus 13 on the left side still, and then on the right side, get 8x plus 20 as I do that distribution. So you should notice now something similar to the first one, the identity equation. At a certain point, we had 4x on the left and we had 4x on the right, and those 4x's ended up canceling. Well, here we have 8x on the left and 8x on the right. Well, as we go to try to gather our x's, and I subtract 8x, I subtract 8x, then I end up with 13 equals 20. And so in that situation with the identity equation, we had a true statement left over, 7 equals 7. Right? Well, here I have a false statement. So that is always false. 13 is never equal to 20. And so that means that we have no solutions. So there's our real answer, is that there are no answers. So again, the answer is not 13, the answer is not 20, the answer is that there are no answers. Again, the answer was not 7, the answer was that there are infinite answers. So what would that look like, right, if I graphed that? Again, we're graphing lines here, so with an inconsistent equation, remember our solutions are the points where the lines touch, right? So here we touch infinite number of times, infinite solutions. Here we touch once at 5, so the answer was 5. So I have no solutions. Well, what types of lines don't touch? We'd be looking at our parallel lines. So that is why there are no solutions, because the lines never touch. If you kind of go back to the beginning here, or the middle, notice that they have the same slope, but different y-intercepts. So that's why they don't touch. So, all right, so those are the types. Not going to be. I'm not going to ask you guys to, memorize the vocabulary here. But it's good to realize you do need to be writing your answers this way if there's infinite solutions, or no solutions, or of course, if there's a solution. A lot of times I like to throw the graphical side of this onto the tests and stuff. Like ask the students if they're understanding what's happening visually. So fair warning. So variables on one side only. How do you solve this? These should be the super easy equations. We're going to be doing some simplifying first. So we're using that distributive property if possible, combining terms if possible, and then adding or subtracting any constants to the other side of the equation, and then finally divided by that coefficient. But these should be super easy problems. We are asking you guys to classify the answer once you're done. So is it inconsistent? Is it consistent? Is it an identity? Is it conditional? So do make sure you do both parts there. So there's no distributing to do. There's no terms to combine on that right side. So I'm just in that solving mode. Again, I'm following SADMEP here. So I'm looking for any subtraction, addition to do first, right? So okay, let's get rid of that -1. Sorry if this is too easy. So that'd be 2x, of course, and then that'd be -10. And then I'm down in that division multiplication level. Oh, I should be dividing by 2. All right, divide by that coefficient. And of course, x would be -5. Well, we got an answer. So that means that this is conditional. And the next one, I'll have you guys do the classification on your own once we see what the answer is. So here we have some distribution to do, so I'm going to start there. That gives me 3x minus 12 plus 7 equals 9. Got some terms on the left side to combine, so that would give me 3x, -12 plus 7 is -5. So there's my simplifying done. Now I'm going to move on to SADMEP. Again, any subtraction addition to do, so I'm going to add 5 to both sides, which is 3x equals 14. And divide by 3. And so then I get x equals 14/3. Don't divide that. If it was reducible, I would ask you guys to reduce it, but I want you guys to leave your answers as improper fractions. No mixed numbers. Okay, no decimals. Improper fractions, please, or fractions if needed. Okay. Then you guys need to classify that. I'll throw that in the ed puzzle. Variables on both sides. So again, just simplifying first. Any distribution, any combining terms needs to be done first. Always simplify before you solve. And then any adding, subtracting. Right, there's my SADMEP. Move variables to one side. Right, gather your variables is what I like to think about it. Then if you're moving all the variables to the left side, then you should be moving the constants to the other side. And that was something I talked about earlier. I decided to move my variables to the left, so my constants move to the right. So separating constants from variables, and then finally divide by that coefficient again. So we start by simplifying distribution, combining terms, and then we gather variables on one side while moving constants to the other side. So I've got some distribution to do. Some more over here. So that would give me 5x minus 10 plus 3x. Then I'd have -6 and then positive 12x. Nope, not 12x. Positive 8x and then a -4. Looks like on the left side I've got 2x terms, so 5x plus 3x would be 8x, and then a -10. So 5x plus 3x. And then on the right side, I've got some constants that I can put, so -6 minus 4, -6 plus -4. Well, I have 8x, and then -6 minus 4 is -10. Ooh, that looks familiar. So now that I've simplified, I'm going to go and solve. I want to gather all my variables on one side, so I'm going to move 8x's to the other side. And as I do that, I end up with -10 equals -10. Again, I should know enough at this point to stop that -10 is always going to equal -10. So that means that this is an infinite solutions situation. And if it's infinite solutions, the classification is identity. Again, we could have known that up here, right? That those are identical, so it was an identity, which means we have infinite solutions. So technically we could have stopped up here if you recognize that. Sometimes people like to go a little bit further. So B, there is no C, just FYI, if you hadn't noticed. Distribute, always want to simplify. So that gives me -6x plus 2 plus x, 14 minus 5x. Have some like terms here on the left. So -6 plus 1, -6 plus 1 is -5x's. 14 minus 5x. Again, should kind of notice something here. If I go to gather my x's on one side by adding 5x. That would give me 2 equals 14, right, which is false. So that means that this is no solutions. And we classify no solutions as a inconsistent equation. Again, those would be my parallel lines. This would have been the like coinciding lines, or lines that are right on top of each other. So, and then I will leave the last one there for you guys to do on the puzzle. So check on that one, like we solved on this side. Essentially something kind of like this. And once we have it like this, then we know what to do. Literal equation is literally the worst thing ever. No. It's an equation that has one or more than one variable in it, but you're only solving for one of them. So a lot of times you see formulas with, that are literal. They have lots of different variables you could plug in. So here we see the perimeter, is equal to 2 times length plus 2 times width. It's like perimeter of a quadrilateral, or maybe like a rectangle. And we want to solve that for w. So how do we isolate w if there's all these other variables? Or this just kind of looks like a made up thing. But a equals 5h plus, or times little b plus big B, right? And so, how do we solve for small b here? So getting that by itself. So we're still using SADMIP. We're trying to isolate that variable, right? It's it's telling us which variable that we're trying to isolate. So how do I get w by itself? I think what the students struggle with this is they get so confused by all the letters. Just treat it like a normal equation, okay? Don't worry that there's a whole bunch of letters. What I see here, p, I don't care about the p since it's on the left side. It's not affecting this at all. But what's the 2L doing to the 2W? Well, it's adding, right? And so how do I get rid of adding? Well, I subtract. What's the 2 doing to the W? Well, it's multiplying. Well, how do I get rid of multiplying? I divide. Well, when do I get rid of multiplying? When do I get rid of adding? And so we're still following SADMIP. Okay. So I should be getting rid of any subtraction addition first, right? Well, the 2L is adding to the W term. So I'm going to subtract the 2L from both sides. So on the left side, we just have P minus 2L. And on the right side, we just have 2w now. All right. And so then now I'm looking at that w and saying, well, w is still not alone. What's happening to the w? It's being multiplied. So how do I get rid of multiplication? By dividing. Sorry. So I'm going to divide both sides by 2. So now that w is by itself over here on the right, I'm going to switch it to the left side just because that's how I prefer to see it. Equals p minus 2l over 2. And so technically I can stop right here. We cannot reduce this the way it's written. We talked about this in section 1.6 because each of these terms do not all share something, right? These two have but 2, but this one doesn't. So I could leave it this way if I wanted, and that'd be my answer. Or if you're really wanting to reduce it, what you would end up doing is saying that this is equal to p over 2 minus 2l over 2, which you could then rewrite as p over 2 minus l. So you could stop here, or you could say that this equals w. Okay. A equals 5 times h times b plus b, little b plus big B, and then I'm trying to solve for little b. What you don't want to do in this situation is distribute, right? I was talking earlier about that, like simplify before we solve. It's actually a bad idea with literal equations to do that. The reason there being that if we do that multiplication, that 5h is going to be on both these things, and we have to deal with that and get rid of it. So on both of them, or you can do it. It's okay. It's not going to ruin things. I think it's easier if you don't do it. So it's more about like, what's that 5h doing right now? Well, it's multiplying, right? Oh, the other thing is if we're thinking along SADMAP lines, right? So, we look at that small b plus big B, that's inside the parentheses. We're not going to deal with that until all the stuff on the outside of the parentheses is gone. So that's the kind of the other thing. Like if I can get rid of stuff that's on the outside of the parentheses, I can make the problem a little bit easier. So that 5h is on the outside of the parentheses, and so I'm going to get rid of it first by dividing it out. So on that left side, I get a over 5h. And on the right side, those cancel. So we're just left with little b plus big B. Well, all the stuff on the outside of the parentheses is gone, so I don't need it anymore. Need them anymore. And then I can just get rid of the big B by subtracting. No, well, that's not a b. What am I doing? And then I would put a minus b over here. So I'm writing that there. It's not going in the denominator though. Sorry. And so again, on the right side, the little b is isolated now, so I'm going to shift that to the left, and then I'm going to write my answer that's on the left side. So all this stuff here, I'm going to write that on the right side now. So a over 5h minus capital B. All right, so sorry for the way I wrote that there. Makes it look like it's a denominator, but I was trying to just tag it on the end. So that's the way it really should look. If you had distributed first, I can show you what that would look like. Again, it's not going to ruin the problem. Oops. But just, it's going to change some things, and maybe it makes it a little messier. And just my rule of thumb is I'm following SADMAP, so trying a different way though. So a equals 5h. So if I just go and do the distribution, 5h little b plus 5h big B. And then I want to isolate little b. All right. So I'm trying to get this thing by itself. And so like last time, I want to get rid of any subtraction addition first. So I would go and say, well, I'm going to get rid of this 5hb minus, oops, make sure I move to the other side of the equation, not twice on the same side. So then I have a minus 5hb equals 5h little b. And then that's not a grade h. Well, now I need to get rid of the stuff that's with little b, and it's 5h times b, so I'm going to divide by 5h, divide by 5h. And so again, at that point, the little b on the right is isolated, so I want to switch to the left side. Equals a minus 5hb over 5h. So again, technically these two answers are the same, just written slightly differently. That's just like what happened over here. I can't just cancel these, that doesn't work. But I could tear the fraction into two fractions and then cancel one part. And so, I would break the fraction apart, and then this would still be divided by 5h, whereas this would cancel, and so I'd be just left with the minus b. So we see that here. The a is still divided by 5h. Then we have the minus b on the other end. So, so different way, the problem wasn't that much messier. I don't like to put something into the problem, like distribute it in, just to have to take it back out later. I had to divide by 5h later. So my first step was to multiply the 5h in, and then I had to divide it out later. So it was kind of like, what's the point? So just seemed like kind of was adding a step, but it's nothing crazy. So there's solving literal equations. Again, just try to solve them like you would a normal equation. Focus on get rid of subtraction, addition first, then get rid of division, multiplication later. Rational equations. So we were just talking about rational equations in 1-6, or rational expressions. So the equations that have fractions in them. Okay, so you notice that ratios, fractions, ratios. Notice that we have fractions here. We have fractions down here on number 5. What our idea here is that we can manipulate this into a linear equation when we're solving, okay? And that basically we're going to take this equation and we're going to mess with it so that it ends up looking more like a normal linear equation, okay? So what makes a rational equation a rational equation is that it has fractions, and fractions are all about their denominators, right? If those weren't there, then those wouldn't be fractions anymore. So if I don't want them to be rational anymore, I want to get rid of the fractions. I want to get rid of the denominators. So if we just think about how do I get rid of a denominator, all right, let's pretend it was like something like x over 3 equals 7. All right, like how do I get rid of the denominator? Well, the denominator is dividing. How do I get rid of division? Well, I just multiply. So if I multiplied by 3, right, that gets rid of that, and now we know that x is 21. So to get rid of a 3 in the bottom, I multiplied both sides by 3, right? So what if I wanted to get rid of a 6 in the bottom, and I want to get rid of a 2 in the bottom? Well, if I multiply by 6 and 2, if I multiply by 6 and 2, and if I multiply by 6 and 2, so if I multiply everything, not just the fractions, everything, okay, multiply everything by that 6 and multiply everything by that 2, then I can get rid of the fractions, okay? So I'm going to do that. And so the way I like to write that, it's a little messy. If you gotta write small. So since I want to get rid of that 6, I'm going to multiply everything by 6. And there is another way to do this, but this is just the way I like to do it. And I want to multiply everything by 2. Okay. And then why I'm doing that, all right? Again, keep your why in mind, right? Why did we multiply by 3 on that last problem? To get rid of the 3. Why am I multiplying by 6? Because the 6 cancels there. Why am I multiplying by 2? Because the 2 cancels there. Well, so then what am I left with? So here I'm left with 2 times x plus 7. Here I'm left with 6 times x minus 2. And here I'm left with negative 4 times 6 times 2. So that distribution on the left side, so the 2 times the x plus 7, as I bring that down, since I'm bringing that down 2x plus 14, since I'm bringing that down all at once, and this is something you've heard me say before, That goes in parentheses. And then I have my plus sign from the problem. And then this 6 times x minus 2. As I bring that down, since it's all coming down together from the same place, it's 6x minus 12 in parentheses. And then equals. And then negative 4 times 6 is 24, times 2 is 48, so negative 48. And we have a nice little equation to finish solving there. Easy peasy, right? So looking at that left side, there's no distribution to do, so the parentheses actually aren't really important at this point. Sometimes they are, so it's just a good habit to bring them down in parentheses, especially if this had been a minus sign, they would matter. But since it's a plus sign, since there's nothing to distribute, I just need to combine those like terms on the left side. So 2x plus 6x is 8x. 14 plus negative 12 is 2. Negative 48. If I then subtract 2, so 8x equals negative 50, and divide both sides by 8. X equals negative 50 over 8, which is really x equals negative 25 over 4. Again, leave your answers as improper fractions, no mixed numbers, no decimals. Okay, so again, to get rid of the 6, I multiplied everything by 6. To get rid of that 2, I multiplied everything by 2. They cancel, leaving me with the 2 times this. The 2's cancel, leaving me with 6 times this. And then over here, there's nothing canceled, so I had to do all that multiplication. Okay, so to get rid of a denominator, I multiply by that denominator. So what if there's variables in the denominator? Makes it a little trickier. When a variable's in the denominator, we still clear those denominators by multiplying both sides of the equation by that LCD. Okay, so that's something I didn't do in the last one. I didn't use the LCD. I just used all the denominators. So I could have made the problem a little bit simpler, a little bit smaller by using the LCD. So LCD there being 6. I could have just multiplied by 6 because a 6 has a 2 in it. It would have canceled the 2. But I like the idea of like seeing how the 2's cancel and the 6's cancel. So again, there is a different way. If you want to do that other way, the kind of shorter way, you can. I'm going to do that on this next one to maybe kind of highlight that, but it's not such a big deal. Oh, sorry, didn't finish this. So we're going to do some factoring, right? Good old factoring to find that LCD. We also have to avoid values that make the variable in the denominator equal to 0. This is a really big deal. Okay, this deals with domain issues. So if we look at that denominator, there's values that we can't plug in for x because there's a number that we can't divide by. Right? We can't divide by 0. So that's where I want to look first. Actually, go ahead and start with that idea. What can't x be? What value of x would make that equal to 0? And by that I mean the denominator. Right? So 3x equals 0, what's x equal to? Right? Well, that must be 0. Or if x equals 0, what's x equal to? Well, of course, x would be 0. So x can't equal 0. Okay? Because if it does, that means we're dividing by 0. Division by 0 doesn't exist. So we can't do that. Okay? So x can be any number but 0. Doesn't mean that x is infinite solutions, but just saying it's allowed to be. Mathematically, it's allowable. Doesn't mean it'll work, but it doesn't just blow up. If we try to make x equal to 0, the problem blows up. Okay? So what's the LCD? We talked about that the other day. What's the smallest thing that all of these go into? All right? And that's more about what's different about them than what's common, right? So we know it's the least common denominator, but you really want to think about what's different about the denominators, not what's the same. So looking at those x's, like I don't want multiple x's in my LCD. I just want one because they both have one x. So that's going to be part of my LCD. And then 3 and 4, what's the least number they both go into? Well, that'd be 12. 3 and 4 both go into 12. That's the smallest thing they both go into. And then what's the smallest thing that x and x both go into? Well, they both go into just x. I don't need an x squared. Okay? They do both go into x squared, but that's not the least common denominator. So the smallest thing they all go into is 12x. Okay? And the reason I want to think of it as 12x is because 12x is made up of a 3, a 4, and an x. So as I go to use it, sometimes I would just say, hey, let's multiply everything by 12x times 12x times 12x times 12x. And that's perfectly fine to do that. And if you do that, you can say, well, I'm just going to look at the numerators. 12x times 2 is 24x over 3x equals 12x times 1 is 12x over 4 minus 12x times 6 is 72x over x. And then I sit here and I reduce. What's 24x divided by 3x? Oh, that's 8. What's 12x divided by 4? Oh, that's 3x. What's 72x divided by x? Oh, that's 72. Okay, and then we have a linear equation, we can solve it. What I like to do, right, it goes back to more what I was doing on the problem above. So what I was saying about this 3 and 4 and x is I like to just, okay, I'm going to multiply by 3 and 4 and by x. And I got to kind of zoom in because it's a little messy. And I multiply by 3 and by 4 and by x. I multiply by 3 and by 4 and by x. Basically what I'm going to do right now is the reducing ahead of time. So the 3 is going to cancel, and the x is going to cancel. And so I'm just left with 4 times 2, which is 8. And here, the 4 would cancel the 4. So now I'm left with 1 times 3 times x, which is 3x. And then here the x's will cancel. And so I'm left with 6 times 3, which is 18. 18 times 4 is 72. So minus 72. So same spot, right? Same equation. Slightly different way of getting there. Here I'm doing the reducing ahead of time. You know, before we kind of did the math, then we did reducing later. You know, it's half a dozen of one, 6 of the other, right? It's the same thing. They get us the same place. Neither one of them is like crazy complex where I really don't want to do it. Oh, that was so many more steps to do it that way. Okay, so kind of choose your method there. Which one works better for you? Again, I think in the end, this one will save us some steps like with more complex problems. When we get down to something like, down here, I would suggest you may kind of try that method. It would probably be a little bit easier. So, but with a problem like this, neither one of them seems any particularly easier there. So, of course, I want to add 72 to both sides, which would give me 80 on the left equals 3x divided by 3. So x would equal 80 over 3. So again, I want you guys to start. Oh, my bad. Right past that. So is that okay? All right. We said x can't equal 0. Well, x doesn't equal 0, right? So that's okay. This is fine. We're going to run into a problem here where these two match, and that's a bad juju. So, but this is fine. We said x can't be 0. X could be any number but 0. Well, x was a number that wasn't 0. Fine. Good. So again, the first thing I want you guys to do is to look at the denominators and say, what can't x be? So I'm just looking here. Thankfully, the denominators are the same. So I just say, x plus 2 equals 0. So that means that x would have to be negative 2 in order to make the denominator 0. So x can't be negative 2. Okay, so start there. What numbers aren't allowed to be answers? Let me stop that. Struggling again. So what's the least common denominator? So, of course we have a little 1 here, but that doesn't matter. So our two denominators that matter are the same already, so that's going to be our LCD. I can't break x plus 2 apart like I did with the 12x, because that was multiplication 12 times x, and so I broke it into its factors. This is not factorable. I can't break it into an x and then a plus 2, okay, because that's addition, it's not multiplication. Okay, so I can't break it apart, so I'm not going to be thinking about it that way. So what I want to do is multiply every term, every term by x plus 2 times x plus 2 times x plus 2. Why are we doing that, right? Remember your why, because we want to cancel those denominators. X plus 2 cancels x plus 2. X plus 2 cancels x plus 2. So what am I left with on that leftist term? Well, I'm just left with 2 minus x. Again, since I'm bringing that down from this at the same time, I'm going to put in parentheses. In the middle here, what am I left with? I'm left with 3 times x plus 2. So I've got my plus, it's going to get parentheses. 3 times x plus 2 is 3x plus 6. And then equals. And then what am I left with there at the end? Right? Well, everything canceled, just that 4. So again, nice easy equation. The parentheses, again, don't matter on this particular problem. Sometimes they do, so you want to be in habit of doing that. And they don't, because that's a plus here. If that had been a minus, again, the parentheses would matter. But since it's a plus, they don't. So I just want to combine my like terms. So I've got some x's. So negative x plus 3 would be 2x. 2 plus 6 would, of course, be 8. Then equals 4. So I subtract 8 over. Would be negative 4 divided by 2. X would be negative 2. Warning, warning, warning. Right? We found out that x was equal to negative 2, but we just said that x can't be equal to negative 2. So the answer we got can't be. So what does that mean about this problem? That means there are no solutions to this problem. The only answer we got, we are not allowed to have, so that means there are no answers. This would come in the realm of when we talked about extraneous solutions in the past. That should be a word that you guys are familiar with from Algebra 2. When we got multiple answers and then when we found out that one of them didn't work, we said, well, that other answer is extraneous, but here's the answer that does work. Well, you can't have one answer that's extraneous. That just means there are no answers. So, but yeah, it just falls in kind of line with that term from before. So. Moving on to the next one. So we always start with that else. What are the values of x that don't work? So I say, well, if 2x plus 1, how do I make that equal to 0? What would x have to be equal to? Well, that means 2x equals negative 1 divided by 2. So x is negative 1/2. So I'm just setting each denominator equal to 0. Subtract 1 over, divide by 3. So those are the values that x is not allowed to be, because if it is, then it makes the denominator 0, one of the denominators 0, and we can't divide by 0, so that's not okay. So if I find out that x is one of these values, then I'll have no solutions again. So start there. What's the LCD? Again, when I look at these, the biggest thing here is that there's addition or subtraction here in these binomials. So these two binomials are not related at all, because that addition or subtraction that could be there. Whereas up here, I could look at the denominators of this and say, okay, the x's are actually related. I only need one x to deal with this, because that's 3 times x, and that's just 1 times x. And that's multiplication, which means that's factorable. But this has addition in it, which means that this is not factorable. So I can't pull it apart and look at its pieces. I just have to look at the whole denominator. I have to look at the whole denominator, and those are not the same. Okay, so that's tricky. And so what would the least common denominator be? Well, if they're completely different from each other, the only way to get them to be the same is to multiply them by each other. And so the least common denominator would be 2x plus 1 times 3x plus 1. It's kind of like if I said, hey, you have 1/5 plus 2/7. The only way to get those to be common, because they don't share any common factors, is just multiplying by each other. So, the actual common denominator would be 35. So it's kind of like that. Since these numbers are what's called mutually prime, they don't share anything in common. To find the LCD, we just have to go ahead and multiply them. So since these are mutually prime, we just have to multiply them to find the LCD, which is fine. This is going to work out nicely for us. So I'm going to go ahead and multiply the LCD. So I'm going to multiply that left side by 2x plus 1 and 3x plus 1. I'm going to multiply that right side by 2x plus 1 and 3x plus 1. Why am I doing that? Because I want the denominators to cancel. So on the left side, that part cancels. I'm left with -3. Can distribute there. Why am I doing that? Because I want the denominators to cancel. So what am I left with? 4 times that. Okay, so taking advantage of that, denominators are gone. We're left with these new linear equations, this nice little pretty equation. If you still have a fraction after this, you're doing it wrong. Okay, so -3 times that would be -9x minus 3 equals, and then 4 times 2x plus 1 is 8x plus 4. Nice little easy linear equation to solve. I'm going to add 9x to both sides. Move my variables to the right, so my constants need to go to the left. So subtract 4, get -7 equals 17x. Of course, divide by 17. So x equals -7 over 17. Divide by 17. So does that equal anything I said it couldn't equal, right? Is -7/17 -1/2 or -1/3? Nope. So that's good to go. Okay. So again, make sure you're considering what x can't be first, and then figure out what x is, and then if those match at all, that means no solutions. Okay. Last one. All right, long video here. Okay. So way back up at the top of this, we said that there could be some factoring involved. It's been a while since I talked about that. So looking at the denominators, can't factor that, can't factor that. Ooh, there's some factoring to do. So what are my factors? Easy AC, what are my factors of -2 that add to be -1? Well, that would be +1 and -2. So this is really going to be that. And so as I look at the denominators, notice that I have an x minus 2 and an x minus 2. And these I can compare, because this is multiplication right here. So I can factor that, right? This, I can look at that factor by itself. And then I have a little 1 times this. So those are common. And I look here and say, oh, this has something in common with this. But these two don't have anything in common. So the idea of well, what if I multiply this by x plus minus 2? Then it would be the same as this. What if I multiply this by x plus 1? Oh, then it'd be the same. Well, this is already x plus 1 times x minus 2. So I don't need to do anything over here. Okay. So because this shares both pieces that we see over here, we don't need to mess with this. We don't need an extra x minus 2 and an extra x plus 1. I just need to deal with the ones that are over here. Again, with numbers, if I said 3 x over 3 plus 2/7 equals 5/21. Multiplying this by 3 and by 7, multiplying this by 3 and by 7, multiplying this by 3 and by 7, right? Multiplying by 3 to get rid of the 3, multiplying by 7 to get rid of the 7. Well, this is a 3 and a 7. So I don't need to multiply by something else, because 3 and a 7 would already get rid of it. Okay? So I don't need to multiply by 3 and 7 and 21, because that 21 here would get rid of that 21 there. So multiplying, if I say my LCD is x minus 2 and x plus 1, so I'm going to say, well, let's multiply that by x minus 2 and x plus 1. Multiply this by x minus 2 and x plus 1. And multiply this by x minus 2 and x plus 1. Now, why are we doing that? To cancel. Those cancel. These cancel. And these cancel. So my denominators all canceled. I didn't need a whole other set of x minus 2s and x plus 1s to cancel. The same ones I used over here were good enough to cancel over here. Okay. It's a little tricky. Oh, dang, I forgot about what can't x be. We'll get there in just a second. So I have a 2 times x plus 1, which is 2x plus 2. That's coming down at the same time. Plus sign. And here I have a 1 times x minus 2, which of course is just x minus 2 coming down at the same time, so it gets parentheses, equals, and then we're just over here on this side, we have just that 1. Let me go back and do that part I didn't do earlier, which was to talk about what x can't be. So I'm looking at each denominator, x minus 2. So it means x would be equal to 2. The other denominator, x plus 1. That means x would be equal to negative 1. So those are the values that if I plugged 2 into here, that would become 0. Then I couldn't do this math, and that means the whole problem blows up. Also, if I plug 2 into here, that would become 0. 0 times anything is 0, so that whole denominator would become 0. That would blow this right side up also. So even though this fraction still exists, the rest of the problem is blown up. If I made this negative 1, that would become 0. Boom. Made that negative 1, that would become 0. 0 times anything is 0. So this goes boom. And this would still exist, but the rest is destroyed, so not okay. So x can't be 2. X can't be negative 1. So let's figure out what x is. Again, the parentheses are not mattering again because this again is a plus here. If that was a minus, we'd have to worry about that. But 2x plus x is 3x. 2 minus 2 versus 0. So 3x equals 1. So divide by 3. So x equals 1/3. 1/3 is not 2. 1/3 is not negative 1. So it's fine that x equals 1/3. Whew. Sorry guys, that was a long one. I do want you guys to change the assignment just a little hair. So I want you to add those 2 other problems on there. These are going to be the literal equations, so you're solving for a variable amongst many variables. The homework's actually pretty easy, so sorry the video was so long. The homework won't be that bad, so I'll stop talking.